All right, so I'm going to do a modeling exercise here. I haven't practiced anything. However, I have put a bunch of stuff on the board so that I hope I can remember to hit some of the salient characteristics of the calculation that we're going to be dealing with. And maybe it'll help remind me, those little reminders on the board will help remind me to say a few things that I want to stress. All right, so modeling. A physical situation, what physical situation? Well, I started as an instructor, as a soccer coach. So I figured we'd start with the soccer situation. So I started coaching when I was 20 or 21, I forget. And the players, high school players, some of them were only a couple of years younger than me. So I made sure I got some discipline by saying Coach V. But now in the classroom, I'm Mr. V. It's what I'm usually called. So Mr. V kicks a ball. I'm having trouble getting balance now. Too many situations, injuries. So I might fall down when I try to do this. But 3 feet high, the ball's 3 feet high. I get it. Nice little touch on the ball. Nice knuckle right on the top of the foot. It goes up 64 feet. Of course, it was 3 feet high when I started. That was the initial height, 3 feet high. And it went up 64 feet to the maximum height of 67. And I'd like you to write the equation of what you think. What calculation are we working with? We work with linear, quadratic, cubic, square root, absolute value, exponential, growth and decay, E notation, LN notation, sinusoid. You guess which one maybe models this situation. And we'll talk about it over the course of a lengthy video here, and it probably will be lengthy. And the reason I'm doing it in video is if I did it in class, I'd lose my first student after 2 minutes. After 3, the first phone would come out. After 5, the first person would walk to the bathroom. After about 7 or 8 minutes, I'd start to see some eyes glass over. And I'd still have, 5 or 10 kids who were paying attention and motivated enough to stick with it. But I would have lost at least half the class in the first 10 minutes. So I'm doing this now. And if you're properly motivated and you want to understand the things we're working with and how we can start to work with them in a more holistic manner, watch the video. And then I might mention, if we wanted to really get into it more deeply in calculus, I asked 50 questions on this one problem. And I'll show you some of the questions I asked. I didn't write all 50, but I'm hoping to maybe make a video of that in a couple of months. To take what we're working here and building on what we're working here. And we'll be talking some of those calculus concepts in this conversation as well. To get the ball rolling. Well, it's not rolling. It's got a nice knuckle on it. Straight up and straight down. Maradona couldn't have done it better. No. All right. So some of the questions that I want to ask at this level are, when's the ball hit the ground? How many skills that we have worked on at this point are associated with this calculation? And how many more skills aren't? Well, that's a great question. All right, so let's have at it. Let's go down here. I got Rene Descartes. Rene is very important to me, and I never really show Rene. So let me show you Rene Descartes. See if I can show you Rene Descartes. There's Rene Descartes. Rene Descartes ready to roll. Okay, see, Rene rolls. And Rene always reminds me to draw pictures. Rene is really good at drawing pictures, and we might draw some here. All right, so let's talk about slopes of a line. What information they tell us about calculations. Well, what's that line tell me? That my table values are going up. As my x's increase, when we count, we go 1, 2, 3, 4, 5, kind of count up a ruler. And this tells me that my y values, which is another ruler, and thanks Rene Descartes for that, I would get a picture. And I can see that something's increasing, something is staying the same, and something's decreasing. And what do? We get curve graphs, all kinds of calculations. And if we draw a tangent to a curve, we get a little feeling for something is going up at this instant. Right? And we've already practiced finding things at an instant, right? We've done a few situations where we've looked at calculations like I don't know, let's see, what would be a good one? I guess I got to do maybe x cubed plus 3x squared minus 4x plus 7. And at 7, I mean, at zero, at time zero, if these were times, we find that that's actually the tangent to the curve at the y-intercept. We'll do that with this problem later and prove that that's true. Okay, but let's get started with what we think this looks like. And sometimes we can use what's called a slope field. And I'll do a partial slope field. I'll do just a partial one for this problem. So we started at 0. The ball was 3 feet high, and I kicked it. So I ask you, where's it going? At what rate? Well, that's a good question, but I know it's certainly going up. I put some force on the ball. Yeah, and it went forever into outer space. Oh, no, it didn't. You're right. You're right. At some point, it stopped going up. And it started doing what? Coming down. And when's it coming down fastest? Well, climb a ladder. Go up 10 feet on the ladder. No, don't go up 10 feet. Go smaller distance up on a ladder and take a step off. And ask yourself, when am I going fastest? Yeah, I think when you hit the ground. So let's just take a look at timeline, right? Takes a while for it to stop going up. I wonder what function kind of looks like that. Well, I'm hoping you're saying a quadratic, right? Because that's what we are going to model this problem with, a quadratic. And we now know that 2,67 is where it maxes. And I think that's one of the questions I've been asking you. What's the maximum value? And in this case, the value would, you could transfer the word height to that word, or substitute the word height and say, what's the maximum height? Maximum height has nothing to do, well, it's got a lot of correlation with the time, but we don't talk about height with the number 2. I don't think that's the unit of measurement that's maximum. I think the maximum is when it hits the ground and then this experiment's over. That's what's called a practical domain. All right, so how much data does it take to write a quadratic? Well, if I had 3 units of data and I said that's a quadratic, let me put this one here. Let's say that's a quadratic. I don't think there's any other way to draw it. Whoops, I hit the corner of the, right? I don't think there's any other way to draw it than to have a cup shape down. Because let's make this one a little further to the left, right? Okay, so I need 3 pieces of data to do what's called a quadratic regression, which means I load those into this thing called a calculator. Boom, 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 boom. I push some buttons and it kicks out a beautiful equation that most people can't read. And a lot of times it's just some of the calculations that come out of that are a little awkward. Right? But in this class, I think we've learned how to write this equation. So the question is, can you write it now? If I give you the picture, thank you, Renee, the picture. So I think the ground level is over here somewhere where y equals 0. Think sea level. When you're above sea level and you're below, you got to have some symbols. Right? My y values are positive when they're above the x-axis. Right? And what's our x-axis in this situation? Seconds. Right? My unit of time here has been measured in seconds. And what do we have over here? Thank you, Renee. We have a y-axis that is measuring things in feet. I don't want to get political now, but this is the USA, We do things in feet. The rest of the world should do it like we do. Well, I got political, I'm sorry, but it's a tough day in our country right now. And I shouldn't even load this up after saying that, but I did. So 0, 3, 267. All right, and so how do I get from here to here? I go up. How do I get from here to here? I go down, and I don't know what time this thing hits the ground, but I'm going to find out because we're going to analyze it. So what's the first thing that I'm hoping people can do? I'm hoping people can write that equation, height as a function of time. Step 1 is, well, we don't need 3 pieces of data anymore, not if we got the vertex. T minus 2 squared. Why am I measuring? What am I doing with T minus 2? T minus 2, I made some notes to myself. T minus 2 tells me seconds changing from 2 seconds. In other words, if I put a 3 in here, 1 second has elapsed from 2 seconds to 3 seconds. And if I put a 0 in here, talking about 2 seconds ago. And 2 seconds ago, I know where I was. I know where the ball was. And I was with the ball. I know 2 things. I was there and the ball was there. All right. And it's going up. But in order to get something other than the equation of the line, looks like this is a squaring process. And we've looked at x squared. We've looked at 0, 1, 4, 9, 1, 4, 9, 0, -1, -2, negative. We've done that tabular work. And we know that this is a version of that. Of course, I want to know where I was at 2 seconds because this is a position statement. And I know where the position of the ball was at 2. It was at 67 feet, which was a max. Yep. But of course, I'm not measuring change in seconds. I'm measuring change in seconds squared. When I put the 2 there, those change in seconds are getting squared. And that's what's being turned into feet. Yeah. Now, how's that happen? Well, as I look out the window, I see a sidewalk and I see, fortunately, I don't see. Well, maybe I do. So, oh, there they are, seconds squared. They're walking up the sidewalk. That's scaring me. Seconds squared. I don't know what to make of them. My first instinct is fear. I better get rid of them. Yeah, that's what we do when we're afraid. We get rid of things we don't understand. So let me get rid of that right now by squaring seconds here and just slashing it out of the problem. Yeah. Yeah, because I don't think when I move to 0, I've changed by 2 seconds. No, I think I've actually changed by 4 seconds squared. Because these are seconds squared. Yeah. And I don't think at 0, I'm at 67 anymore. I think 0 minus 2 squared is 4. And if I get rid of those 4 squared seconds, thank you, they're gone now. They're gone. I think I want to get from 67 to 3, which is down 64 feet. And I think we practiced this. And if I'm not mistaken, when I divide that, I get minus 16, which is a nice number to work with, which is why I picked these numbers. All right, so what are the skills we've practiced? I've asked you to expand that. Now, be honest with you, the 50 questions I do in calculus, this is the hardest one. The students don't know how to do that. And they understand it because it's not stressed in any textbook. Rise over run squared, you don't see very much. That's unfortunate because it's the most important aspect of the question and the problem here is understanding that, the conversion process. But what we practice in the classroom is to expand that. I hope you can. I hope you know the order of operations now. I hope you know how to square a binomial. And I hope you know how to put that together so that you can write h of t equals minus 16t squared plus 64t plus 67. Hoping you're learning that in this class, and I'm hoping that's easy for you to do now. And for most people, you're getting it right, and it is easy, and it wasn't 2 months ago. So that's a good thing. Now, if we want to get into it and plant a few seeds from a calculus standpoint, I've done this because I think it's important for you to see. So if we put a 0 in, you get 0, 0, 67. And if you put 0.001 in, you get 0.0000 negative, excuse me, negative 0.000456. I believe you get that. Yeah, I think you get 6 decimal places, and I think you multiply by that 1 at the end by negative 16. And in here, if you put it in there, you get 0.064, 0.001 times 64. You just move the decimal places You got 3 decimal places. And 67 is still 67. So ask yourself, what's changed? There's change there, there's change there, there's change there. And is that change positive or negative? I think it's positive. I think this wins the day. If you're seeing this number change, I've mentioned this many times in previous videos, please send me an email, give me a call. I'm available. We can get some help. There's no change here. I could have done more decimal places. What's going to happen to this amount? It's going to get closer and closer to 0. But one thing is not going to change. That divided by that is 64. And that, my friends, is the rate of change of the ball. Once it left my foot, it was going up at 64 feet per second, and it went up into space. Oh, no. Yes, there's a constant force, and you say gravity. You'd be right. Well, let's expand this further and see what materializes. H of t becomes minus 16t squared plus 64t plus 3. Must be a coincidence that that's the rate of change of the tangent line at the y-intercept. Got to be a coincidence. Can't imagine that that would happen each and every time I looked at a polynomial, that this would be the equation of the line tangent to those curves. Boy, wouldn't that be nice if I knew that happened every single time for a polynomial. Oh, well, let's keep going. So then what do I ask? What's a problem that's on every test? Putting that in graphing form. Well, let's put it in graphing form and see what we get. Okay. Well, I think minus b over 2a comes to my mind. Hoping it comes to yours. Minus 64 over minus 32 gets me 2. Another coincidence. The number 2 appears. Very important in this problem. Why? What a coincidence. Yeah. And let's put 2 into the, let's just see what happens when I put that time into this equation. I get minus 16 times 4 plus 64 times 2 plus 3. Well, let's do that out. That's minus 64 plus 128 plus 3. Oh, we've been looking at a pattern here. At the vertex of a quadratic, a 2-to-1 pattern opposite, and I'm seeing it. Must be another coincidence. Oh, and that's 64 plus 3, 67. God, the coincidences are just flying off the board here. They're just flying off the board. I guess that got me my maximum height. And of course, I'm introducing what now is another question on your test. What's the range? What's the range of this function? Well, there's 2 ranges. There's one practical range, the actual experiment, and then there's a mathematical range. The mathematical range is y is less than or equal to 67. That's all my heights. They're below 67. But practically, I think they better be bigger than or equal to 0 because it hits the ground. That's a practical range. Oh, that's good to know. All right, so what other problems do we have here? Oh, when does it hit the ground? Oh, that's right, we got a picture here. This is one of the questions, and we just figured out a is negative 16, right? That was the a term, and said, oh, when's it hit the ground? At what time? I think it's 2 plus the square root of 67 divided by 16, because I think there's a real crash right there. I don't think it's imaginary. I think the ball is going to hit the ground. I mean, I've done it a lot of times. And when I haven't tried to catch it on my foot, which is another good skill to practice, hit a ball up 67 feet, try to catch it. It's a good practice. So instead of you guys that are juggling putting spin on the ball and juggling for, whatever, and that's great. It's a lot of fun. But if you want to improve your game, try to catch it. Yeah. So that's when it hits the ground. Of course, I might want to take a feeling for it by putting the square root of 64 over 16, because I know that's 4. And that's 2 plus the square root of 4. But this is just a little bit bigger. Yeah, but I do believe after 4 seconds, we're back to 3 feet high. And I think just a little bit more than 4 seconds, it hits the ground. And if I wanted to get a feel for the rate of change there, I could get a little feel for it by doing the change in y, which is 3, right? 3 minus 0, 3 feet, and I have to have the change in x, which we just found was 2. Well, anyway, I'm losing my train of thought here. X2 minus x1, this is x2, right? Minus x1, so I guess I'm 2 plus the square root of 16, 67 over 16. I don't want to get caught up in something minutia here, but that should give me a little feel for feet per second. And then I'd probably find out that I don't want to be that ball coming down, and no, it would not be a good thing. So we could do that, but I didn't ask that, except I just talked about it. What else did I want you to talk about? Oh yeah, I guess we look at how we could find that calculation again by saying, okay, we know we got minus 16, t minus 2 squared plus 67, and I guess I'm trying to figure out when it hits the ground. And we're trying to learn how to do minus 67 divided by minus 16 plus minus the square root of 67 over 16 equals 2 plus or minus the square root of 67 over 16. Yeah, I guess we're trying to match that up. Say, that works. Yep. So is there anything else I wanted to say? Probably not. Other than this asks you to put a whole bunch of questions together that aren't, let's put 10 problems in graphing form, where you memorize and then just do. I think mathematics, to understand it, you want to link problems together, which brings me to one of the questions I asked on the test. I threw you into a whole new mode, and I wanted to see if anybody could figure that out. Get a little practice with, let's hide a few questions. Where else have I hidden a few questions? Factor x to the 4th minus y to the 4th. There, I'm hiding a question to really find out if you know how to factor the difference of 2 squares. And most of you did very well. X squared minus y squared times x squared plus y squared. Very good. Then you stopped. And that told me you can't factor the difference of 2 squares yet because you didn't recognize it when I hit it. If you recognized it, you would have said x minus y times x plus y. So what did I do? I hit it on the next test. I gave you 16x to the 4th minus 1. Gave you another try. Not there yet. So I'll give it to you on another test. But this time I did x to the 8th minus y to the 8th. And now I'm hiding this one. Does this really, really fool you? I don't know. Log base 5 to 25 is 2. That was day 1. We said you can do what with that? You can write 5 squared equals 25. Right. Well, can't we write x squared equals 2x plus 8? If we really are looking at this critically, that's the new buzzword. Educationally, we got the pendulum swinging. We always go from try something there, try something there. Right? Well, I'm not trying anything other than giving you what it is, continuing to give you what it is, having you look at it, try to get your attention, try to get you to think about it, try to get it so that it just is in your pocket and you can use it. So I'm hoping that you know to do this. And we're closing a gap from Algebra 1. And I'm hoping you do this. And I wanted to have the conversation that only x equals 4 works. Why? Because the base of logarithms and exponentials have to be positive. Now, I could have said that earlier in the term, but I think it was more important to be able to rearrange these things and get the conversation started. All right, so a lot of questions are in those tests that are designed to get you to move along in a proper direction, which means upward slope. And it would be nice if we could accelerate that. And that's when the 50 questions from calculus occur. What are some of the questions? I'll just go down. Let's go, Renee. I think I talked about most of what I wanted to talk about. So, the 50 questions in calculus, well, we usually finish the 75% in the first 2 weeks. Do students have a handle on 75% of an AB calculus course in 2 weeks? No, it takes time. But we start the conversations, in a lot of different areas and try to tie things together and continue to have those conversations. And after midterm, we're usually done 3 days after midterm with, rotating volumes of revolution, things like that, in terms of X, in terms of Y. We're done with everything. And then we can spend the whole next 2 months doing multiple choice and free response and modeling situations. And one of the modeling situations, this one. And I get to ask, what's the velocity? And I've gotten here with Algebra 1 classes, and we're ready to actually look at it now. And we've actually have looked at it a little bit, plant some seeds. What's the acceleration? How do I write h of t as, or what does the area under the velocity curve from 0 to 2 represent? How about under the acceleration curve? How about we look at proving the maximum? What proves that 67 feet was a max? Well, we got a second derivative, a first derivative test, and that deals with concavity. We learn how to write h of t as an integral expression. We work with the mean value theorem for derivative. I can go on and on and on. About 50 questions on that one problem. We probably could teach the whole calculus class on this one problem, except for the volumes of revolution. Can we get a related rates and optimum? I don't know, but 90% of the calculus class, first year calculus class, would do well to study one problem and get a feeling for the concepts and what you're working with. And I'm hoping to maybe make that video in a couple of months. But right now, I'm wedded with a Algebra 2 class, and that's where my focus is. And part of that class is moving people to grade level and beyond. And part of it is, getting to that grade level because of COVID and collapsing system over here. We have gaps. It's got to close those gaps, and we are very happy with the progress this class is making. I'm delighted. Okay, but that doesn't mean I'm going to stop pushing. I'm going to keep pushing and hopefully just give credit for credit when due. When somebody understands a question, I don't care at what point in time in the term, full credit. If you can graph a polynomial, if you can take y equals 2x squared minus 16x plus 7 and graph it correctly, then as far as I'm concerned, that's a check mark for that topic. And I have a certain number of check marks I want to see. And that's how I grade. All right, so I've said a mouthful. I would love to do this in another month or two, and maybe we will get to it. We'll see. All right, so that's a little explanation about how we're doing things in this classroom, and some students will look at this and think about it, and if they do, I think it will help move the needle forward, up, just like that ball. And for those that don't, well, that's a whole nother discussion about learning how to learn. Okay. Yeah, sir, I hope you're staying safe and warm. All right, and everybody else as well. Now, I appreciate Yasser. Yasser corrects problems when I get absent-minded, and I actually think about a lot of things that he talks about, and I ask myself, well, what could we do to help people see that? And so it's been helpful to me. So I appreciate that. All right, now where the heck is the cursor? I heard the cursors. You might, when they first came out with computers, there was a big discussion on NPR today about mouses, mice, mices. We used to have to roll this thing around to move the cursor. Dating myself. All right, toodaloo.